All right. Welcome everyone to the final Origins talk of this semester. Kevin Williams is our speaker, and then take it away.
Hey everyone, thanks for joining. I'm excited to introduce Gabe Weible. For those of you who don't know Gabe, he was an undergraduate here, and I'm happy that he's decided to continue on as a graduate student and continuing working in our group with data from the LBTI on exoplanet imaging and brown dwarf imaging, and that's some of what he's going to be telling us today with orbital modeling of HII 1348B. Take it away, Gabe.
All right, thanks, Kevin. Yeah, so I'm excited to talk about this project, something I've been working on for a few years and finishing up now. We'll start with just a brief introduction. I'm going to use this term substellar companions as a catch-all term a lot. So I'm throwing in brown dwarfs and exoplanets, especially gas giant exoplanets, into one term. And that 13 Jupiter mass distinction is usually what's used to separate these objects. But that's not based on how they form. It's just based on their mass and the mass at which they're expected to fuse deuterium. So it's very possible to have objects smaller than 13 Jupiter masses forming through a direct collapse of a molecular cloud, more like a star. And it also could be possible to have brown dwarf mass objects form in a protoplanetary disk, more like a planet. So a lot of times, generally, I'll just call them substellar companions for seeing some glowing ball of gas that's not a star. The discovery of exoplanetary companions, especially to stars, has been a huge new field in astronomy starting in the 90s. Most of these detections coming from transits and radio velocity techniques, observing the host stars and inferring the presence of a planet from its effect on that star, either on its photometry when it's transits or on its spectrum as the star is Doppler shifted. And these little tiny dark blue slivers are discoveries from imaging, from directly capturing photons from exoplanets orbiting stars. So this technique is clearly not the most efficient at discovering large numbers of gas giant planets, but it does let us see some important insights into them that we can't with other techniques. And it also probes a different population of companions than transits or radio velocity. So these blue stars are concentrated at high masses, from large superjovian planets to brown dwarf, and at very long orbital periods, wide orbits. So these planets can't be seen with other techniques currently. And the population is very small, but we're starting to build up something that we can get statistical results for. And this brown dwarf companion that I'll talk about today is one such directly imaged companion. Now, high contrast imaging techniques are necessary to do direct imaging. You can't easily just look at a star and take a long integration and expect to see a planet. We're biased to finding these wide orbit, very young planets. Wide orbit so that the projected separation is larger, which is useful for whatever resolution our telescope has for spatially resolving the planet. And young companions are preferred because these observations, as of now, are almost entirely done in the infrared. So we're just looking at the residual heat of these planets and brown dwarfs. They're cooling down after they form, so the younger that we catch them, the brighter they're going to be. And also, since stars have their black body spectra peaking in the visible, we get a more favorable contrast ratio in the infrared. And thankfully, we have nice adaptive optics technology that has been developed, especially here at the University of Arizona over the last few decades. And that allows us to really get the most out of large telescopes beyond just their light collecting ability, but really getting the high angular resolution and contrast necessary to find these objects. So we use coronagraphs to directly block the star in the center of our image and reduce its glare, or there are also post-processing techniques we can use to remove the point spread function of the host star after the fact. And those are the techniques that I've used in my study. So generally, this is very difficult. We've seen there's small numbers of these planets that have been found with direct imaging. And this shows the detection limits of a few different current and proposed instruments for high contrast imaging. You can see JWST as the pink dashed curve on the right, which is very, very sensitive, but it's limited by its angular resolution. The inner working angle can't find planets that are too close to their stars. And we're still well above the limits of our solar system if it were to be observed from far away. So the reasons we really want to do this, even though it's hard to directly image planets, we can see things that we can't with other techniques, including direct spectra of planets. So you can do transmission spectroscopy, but often you're highly limited by the noise in the star spectra. How well do you understand your star? By spatially and spectrally resolving an exoplanet separate from its host star, we can mitigate a lot of those effects. We can also see some tracers of formation in really young protoplanets. So this image here of PDS-70b, there's H alpha detection linked to accretion onto the protoplanet on top of the blue infrared disk and planet observations. So there's likely a circumplanetary disk around this very young system as well. And finally, I'll move on to actually talking about my project, HII 1348B. This is a triple system in the Pleiades. We can zoom in on this HST image of the field, and we find this little K-type main sequence star, which is actually a double-lined spectroscopic binary. So the Pleiades is a bit over 100 million years old. That's older than a lot of the young stellar associations and moving groups that direct imaging often targets. It can be as low as a few million years, but it's still much younger than field-age objects where these substellar companions will have cooled really appreciably. So it's sort of an intermediate age regime, slightly further than the closest moving groups, like the Beta Uma moving group, but still not too far that we can't hope to spatially resolve companions. Now I'm working with infrared imaging in the L or the L prime band. This is an atmospheric transmission window centered on about 3.5, 3.7 microns. One of the good transmission windows in the infrared that we can observe with the ground, even though there are high background levels, which we mitigate with our image processing. The observations that we're looking at today were taken with the Large Binocular Telescope, specifically the LBTI interferometer instrument. So these are not interferometric observations, but we're using a single detector mounted between the two apertures and taking both PSFs from both 8.4 meter primaries, sending them up to the two adaptive secondaries, and then back down to be imaged on a single detector. We have almost 3 hours of integration, and that spectroscopic binary star is spatially unresolved. We see it as a single PSF that allows us to remove it with post-processing more easily. And it's also unsaturated in our imaging. We can control the integration time to do that. And that also helps with post-processing star subtraction, where we're not using a coronagraph. So we have 4 images here. These are fully processed from our raw integrations. The reason we're seeing 4 is we're taking both apertures, imaging them on the same detector in different locations, and then physically nodding the telescope between positions intermittently, going back and forth and shifting both PSFs. So we can functionally split our data set 4 ways, and these aren't completely independent observations. There's only 2 apertures and only these 2 telescope positions, but they are somewhat independent. The light is taking different optical paths through the system, and 2 separate primary mirrors and adaptive secondary mirrors, 2 different distortion corrections and plate scales for the 2 apertures. So we'll treat these four separately and then combine the results at the end, ensure that our astrometry and photometry are self-consistent across these observations. So we see this brown dwarf companion separated at a bit over 1 arcsecond. And it's oversampled. The L prime PSF is oversampled here, which also helps us in our astrometry. So we'll do this astrometry and photometry 4 different times to try to pinpoint this companion that will feed into our orbital modeling, whereas the photometry will help us estimate its mass and also fit to its spectrum. We use 2 different algorithms to get the astrometry of the companion. The first is a more simple centroiding, fitting Gaussians to the marginalized PSF profiles. And the second technique, which is a bit more robust, allows us to forward model the astrometry and photometry simultaneously through our observations. So we take a model of the point spread function from the host star PSF, we inject it negatively from the image around where we expect the companion to be, and we can vary the XY position and also the negative brightness to try to minimize the residuals of the companion. And after subtracting the companion from each image, all of the images can be processed together through the host star subtraction so that the end result shows essentially no companion, as if it didn't exist. So this is one processed image from one aperture of the telescope at one nodding position. And after we subtract it out, it looks like it disappeared. So when we see that the residuals are minimized, all we see is the background noise. We can be very confident that we've pinpointed the location of the companion and also estimated its brightness very accurately. This is the astrometry that we come out with at the end of the day. So we've zoomed in on a single pixel on the scale of the Elmercam detector. And both techniques and also among measurements with either technique, the astrometry is consistent to under a single pixel. So this makes us very happy. We don't have to worry about problems or discrepancies between the 2 apertures, which could have totally unrelated errors in their plate scales and true north solutions that could throw these points all over the place. But we're very confident now that we have processed both apertures and both nodding positions consistently, and we can be confident in those distortion solutions. Yeah, 1 pixel here is about 10 milliarc seconds. So somewhere around 5 milliarc second errors in either direction. For the photometry, which was estimated at the same time from those negative injections, we also get 4 different contrast ratios. So we're not doing absolute photometry, but we're getting a direct measurement of the contrast by scaling the host star's brightness as we negatively inject companions and minimize those residuals. And then what we do is we take absolute photometry of the host star, in this case from the WISE mission at 3.4 microns with a small color correction to L prime. And then we can actually get an apparent and an absolute magnitude of the companion. The end result of the contrast ratio is relatively favorable as far as direct imaging goes, about 1 part in 100. And from that brightness, we can also estimate the mass of this brown dwarf by comparing to evolutionary models. So we know the age of the Pleiades very well. So we know how old the brown dwarf companion should be. We know the distance very well from Gaia. And we also have these theoretical models of how we expect brown dwarfs and exoplanets to cool over time. These models will differ in the internal energy that they assume these objects to begin with. And they will also evolve slightly differently and evolve differently according to the mass of the companion. We'd expect more massive brown dwarfs and planets to cool more slowly than the less massive ones. And we estimate the mass at about 63 Jupiter masses. So that's right at the upper range of brown dwarfs being substellar, the hydrogen burning limit being somewhere around 72 Jupiter masses. And currently we're working on estimating this mass more robustly from a bolometric magnitude instead of just from the L prime photometry, which would be more susceptible to model dependent differences in evolution. Now, from that estimated mass, we can do a similar procedure, injecting positive companions into our data, recovering them, seeing what signal to noise we can find them with, and then also comparing those brightnesses that we recover to masses at the same age and distance. We find that anything larger than around 10 to 12 Jupiter masses we would have expected to image in these observations, down to about 1/4 of an arc second. So there's still the possibility for super Jovian, any sub-Jovian exoplanet companions to reside in the system that we haven't been able to detect. And this is limited by the integration time and also the inner working angle of our star subtraction and how quickly the noise goes up with decreasing projected separation. So from the astrometric measurements that we made, we sought to model this companion's orbit for the first time. We used this Orbitize package in Python, specifically designed for fitting orbits of long period companions, especially when you've only observed part of an orbit. If you've observed the complete orbit, you can get a perfect solution. If you've only observed part of it, there's going to be a distribution of possible orbits which fit the observed astrometry. And we had 4 prior epochs of relative astrometry that this companion was observed at by other teams, dating back to 1997. So in this case, 23 years baseline of relative astrometry. You can see those results summarized in this table here. And fitting orbits to these values, we fit 30 million orbits. And we state our priors here that we take on some of the orbital elements, mostly uniform priors, but a sign prior and inclination, which is necessary to uniformly sample on a sphere, and a log uniform prior on the semi-major axis, which is shifted towards lower projected separations and then has a long tail to further projected separations. So this plot is just demonstrating the convergence of our MCMC fitting. This is after we have thrown out burn-in samples, an equal number, 30 million samples. So this plot is showing the mean and also the mean absolute deviation, which is a measure of the width of these distributions. We have 6 orbital elements, also the total mass of the system, and the parallax, which are 3 parameters in our fitting. So from that stationary distribution, we can draw a sample of potential orbits of this brown dwarf. So these are 100 randomly selected orbits from the posterior distribution. These aren't necessarily the best fit orbits or the maximum likelihood orbits, but it's meant to demonstrate the width of possibilities given the constraints we have. So we're only observing this dark blue region where we see projected separation increasing and also a decrease in position angle, which corresponds to clockwise on sky rotation. We can't differentiate whether the companion is moving towards us or away from us in radial velocity. So there is a degeneracy in these solutions due to that. And this is a large corner plot. Sorry, it's hard to read all of the labels here, showing the posterior distributions of these elements. And what we find is that it is on this wide orbit, which we knew already from the projected separation, semi-major axis of around 140 AU. It's also likely highly eccentric, around 0.8. So there is this long tail to eccentricity. That's the second column here. But it's heavily biased towards being an eccentric companion. And then other results for the orientation of the system. One further analysis we wanted to make from our L prime photometry was to compare with previous photometric measurements in other band passes. So from the prior observations, we got our astrometry. There were also apparent magnitudes in the near infrared, JH, K, KS. And putting these together, we want to confirm the spectral type assigned by the discovery paper for this companion, Geisler 2012. They identified it as being best fit by an M8 spectrum template, but with some uncertainty towards higher or lower spectral types. We decided to use BT settle atmospheric models. These models span a wide range of effective temperatures, but we have restricted the metallicity and all the elemental abundances to solar values from the SciFis team. And with this grid, we have a range of log G from 2.5 to 5.5, and we restricted the effective temperature search between 2000 and 4100 Kelvin. And for each model, we minimize chi-squared by varying the radius of the companion that we assume, which scales the spectrum vertically. So this is the end result of fitting this this grid of models. And we've also interpolated between adjacent models to better sample the parameter space. So we have effective temperature of the model on the x-axis, surface gravity on the y-axis, and the vertexes of the grid here are the actual models that we've been able to download from the team, and between them we've interpolated. This identifies a maximum likelihood at a hotter temperature than we would expect, around 3100 Kelvin. And the surface gravity is not well constrained by fitting to the broadband photometry, which is expected as we're not very sensitive to some of the molecular and elemental features that could constrain the surface gravity better. To get a better understanding of this distribution in the full 2D grid, we've actually interpolated these likelihoods. So we tried not to introduce any additional structure between the models that we tested, but to keep sort of a blurry blob that follows the likelihoods that we estimated. And we then assigned a prior uneffective temperature given the previous spectral analysis. So for M8 plus or minus 1, we assumed a prior of around 2600 Kelvin plus or minus 190. And applying that to the likelihoods of fitting to the photometric measurements shifts the distribution in effective temperature to lower temperatures as we would expect. But it also makes it more highly bimodal in surface gravity, favoring the very top and bottom of the grid, 2.5 and 5.5. Those are the two modes of the posterior distribution that we find. And this allows for a wide range of implied masses from the spectrum. You can take the radius of the fitted model and the surface gravity to assume a mass. And at the lowest end, this assumes something about a fifth of a Jupiter mass up to hundreds of Jupiter masses. Both of these modes we would expect to have unphysical masses. This 1/5 of a Jupiter mass we would expect to be much, much cooler at the age of the Pleiades. And similarly, at 180 Jupiter masses, that would actually be a star and no longer a brown dwarf companion. And we would also have expected a different spectral type. So this plot shows those two modes plotted with our photometry. And what we see is that we really just can't constrain the surface gravity from the photometry alone. So while these two models with lower surface gravity in this pink color and in purple higher surface gravity do show different features, especially in the H band, there's this steep spike. The broadband photometry is not sensitive to this slope. It catches either side of it. So if it's lower on one end and higher on the other, all averages out the same when you integrate across the band pass. So really, we're only sensitive to the effective temperature with broadband photometry. And unfortunately, the previous near IR spectra were not available for us to fit to. Now, actually estimating parameter values from the likelihoods and posterior distributions that I showed earlier, we did an MCMC analysis, 20 different walkers, each taking 1 million steps and discarding some burn-in. And the marginal distributions are shown here in the diagonals of this corner plot. And we also see the bimodal 2D distributions in the corner there. So maximum likelihood, or just likelihood estimation on the left, and the posterior estimation on the right. We do find, assuming the effective temperature prior from the previous spectral type, a temperature that is generally consistent with a mid to late M companion. So this at least shows that our L prime photometry can be consistent with the previously determined spectral type, but with no further constraints on the surface gravity of the companion. Now, putting together all the different things I've shown today, we found a very wide orbit for this brown dwarf, likely on a very eccentric orbit, and it's on the high end of the brown dwarf mass range. And the characteristics of its orbit are typical of multiple star systems. We see many eccentric wide stellar binaries and triple systems. So we infer that this brown dwarf companion likely formed akin to a star from a gravitational collapse. We can't say exactly where that collapse would have occurred. It could have occurred directly from the molecular cloud, could have occurred within a protostellar disk or circumstellar disk, but there was likely a dynamical interaction after the formation, which sent this brown dwarf on its highly eccentric orbit. And the inner binary, the spectroscopic binary, is also eccentric, which is interesting. And haven't shown a plot here, but there's likely a small mutual inclination between the wide brown dwarf companion and the inner binary. So this suggests some sort of interaction, a near escape process. And putting this into perspective with the larger population of orbits of giant planets and brown dwarf companions, this paper from Brendan Bowler in 2020 showed that higher mass brown dwarf companions as a population do appear to be more often on these eccentric orbits, where the smaller giant planet population, in this case, cut off below 15 Jupiter masses, are much more common on not necessarily circular, but marginally eccentric orbits. So fitting into this population on the right here, HII 1348B does match these expectations, and this may hint at a difference in formation channel between these populations. I would expect some overlap of the lowest mass brown dwarfs and the highest mass giant planets, but at this point, it's hard to say where that distinction is or what the initial fragmentation mechanism may be, even for a large gaseous companion that couldn't have formed through something like core accretion, which we expect the lower mass gas giant planets similar to those in our solar system to have formed through. So as a summary, we've detected this brown dwarf companion in the mid-infrared L prime band for the first time, extending the relative astrometric baseline to 23 years. And fitting the first model to its orbit, we find this likely very wide, very eccentric orbit. We estimate its mass from the mid-infrared photometry and find that it's at the upper range of the brown dwarf mass scale. And we infer that this likely formed similar to a triple star system, which went through a dynamical interaction sometime in the last 100 million years or so since its formation. And consistent with this mid to late M spectral type, HII 1348B would be expected to be substellar at the age of the Pleiades. So this work is going to be published very soon, I hope, preparing to resubmit to the Astronomical Journal. Lots of my collaborators here, some of them in the room, and I'm sure you're aware of lots of Steward Observatory and former Steward Observatory people. So I'd like to thank everybody who's helped me with this project over the last few years. And thanks for listening.
Thank you very much, Gabe. Do we have any questions in the room? Yes.
What are the prospects, especially with LBT, doing an H-band spectrum to distinguish those widely different gravities?
That would certainly be very useful. In the H-band, like you said, is where we see the biggest difference in features between the low and high surface gravities. I haven't looked at what sort of observing conditions would be necessary to do that. But we have discussed doing some sort of integral field spectroscopy to try to constrain these atmospheric parameters better.
Sarah?
Yeah, it was really nice talk. Thank you. I was going to ask about this plot. Are those varying points, your left, right, and 1, 2?
Oh, right. Yeah. So these black and gray points are the observed photometry. So our L prime here is averaged over the 4 images, 2 apertures and 2 nodding positions. And then the purple and the pink points are synthetic photometry from integrating these model spectra over the bandpass of the filter. And so that's what we're actually directly fitting here, is we're fitting the purple and pink points inferred from the spectrum to the observed photometry. That's why we end up not being sensitive to a lot of these features, because we're fitting integrated brightness that's washing out these peaks and spikes to lead to a non-determination of the surface gravity.
Are there any questions online? You can either raise your hand or type a message in the chat.
So I was just wondering about, maybe the binary messes this up, but it is possible to get a mass from the primaries, the astrometry of the primary and radial velocity.
Right. Yeah, dynamical mass constraint would be great. We haven't looked at the Gaia Hipparcos acceleration. It's possible there's something there. In theory, it should be possible to fit for both a radial velocity signal of the primary and a secondary at the same time. I would worry about the period of the secondary's effect. The orbital periods are expected to be on the order of thousands of years. So I think it would be a very slight linear trend on top of the binary's orbit. Yeah, I think it'd be tricky, but it may be worth looking into.
Very good talk. I don't know if you try to do that, but do you have any idea if the age of the Pleiades is comparable to a multiple of the timescales of encounters between the stars of the cluster, in order to try to explain the widening rate of it?
Right, that's a good question. Yeah, I'm not I'm not super knowledgeable on sort of the past history of the Pleiades as a whole. It certainly is this dense star forming environment that I would think would be favorable to interactions that could lead to these sorts of scatterings and near ejections. But I'm not sure what the typical timescale would that be, or when in the past this would have been occurring.
Did you come to any conclusions about the various methods that you were using to determine the temperature and or I guess more particularly the gravity, like because obviously, I mean, your summary says that you favor the large, but larger radius, but for gravity, but.
Yeah, I think we really can't give a strong conclusion on the surface gravity from this result. I think confirming the effective temperature being consistent with the spectral type is possible. I think it would be useful to investigate other atmospheric model grids, especially since the highest posterior probabilities are at the edge of this grid. I think it would be possible with a different set of models to make a more substantive claim of how confident we are in the gravity. But ultimately, I think it's going to take a real spectrum with some resolution to be able to constrain anything besides the effective temperature.
Yeah, I was wondering about with the models, like thinking of like since those they're like but I don't know if the Sonora Owl goes hot enough, and Sphinx and Phoenix Aces, are those all potential models you could use?
Yeah, I haven't done a full sort of census of which models are possible. Certainly some of them don't go up to temperatures high enough that we would like and are optimized or specialized for planets, and some of them don't go low enough and are specialized more for the brown dwarf star side of things. This like ML transition is kind of a cutoff. So we had looked at a wider set of BT settle models over more abundances, but then at between 2500 and 2600 Kelvin, there's a sort of discontinuity in the grid, and there's no variation in metallicity below 2600 Kelvin. So we wanted a grid that we could uniformly sample in all of its parameters around where we expect the companion to, or where we expect its atmosphere to lie in that space. Yeah, definitely worth looking into and seeing how different or similar other grids may produce results to these.
Thanks, Gabe. I'm wondering if you can comment on how unique this object is. Are surveys of the Pleiades complete to these objects? Are there others of them that are known?
Right, so there are two other imaged brown dwarf companions in the Pleiades. So this is one of three of sort of comparable systems. There are no directly imaged true exoplanets in the Pleiades, and all three of the brown dwarf image companions are on the higher mass range, around 50 to 60 Jupiter masses. So there's definitely a lot, many lower mass companions that are likely residing there that haven't been imaged. Only a couple of transiting or radial velocity planets in the Pleiades also, from what I could find. It's not really in the Kepler or the K2 fields, not in TESS.
Any other questions in the room? Last call for any questions online. Let's thank our speaker again.